Aerospace engineering is an area in the engineering field that deals with the design, development, testing, and production of various sorts of equipment, including airplanes, spacecraft, and any other related products. Within aerospace engineering, there are two main branches that work with different kinds of aircraft. Aeronautical engineering focuses on flight within the Earth's atmosphere, while astronautical engineering is instead related to the science and technology of spaceflight. Aerospace engineers mainly work at large companies such as Boeing, Airbus, or Lockheed Martin, or alternatively for the government. Usually, these kinds of engineers develop and experiment with technologies that can be used for many applications in aviation, including transportation, communication, exploration, and defense. Individuals studying aerospace engineering at university mainly work with subjects that are classified under dynamics, a branch of mechanics, including solid, structural, and fluid mechanics, thermodynamics, aircraft design, and flight dynamics. In this video, we will be presenting and explaining many theoretical concepts linked to aerodynamics and more generally fluid dynamics, as these two areas of study are fundamental for any aspiring engineer in the aviation sector. Aerodynamics is the study of the forces and motions of an object, or body, passing through the air. When two solid objects collide, they do so by transmitting forces through the points of contact. This is not the case when a solid interacts with a fluid, due to the air being able to change its shape and wrap itself around the object. Due to this, the mechanical forces that result from the interaction between solid and gaseous substances occur at every point along the object's surface, and not in a singular location. This happens because of the fluid's pressure. Pressure is a scalar quantity, meaning that it does not have a direction but only a magnitude, or size. Pressure is, in this case, related to the momentum of molecules in a fluid, and can be defined as being equivalent to the force applied on an object divided by the area of the surface. Pressure is always perpendicular to an exact point along an object. Let's take an airfoil as an example of a body affected by pressure. This object has a particular teardrop-like shape, as it allows it to generate great quantities of lift, of which we will be discussing in more detail later on. If we were to take the cross-section of a plane's wing, we would notice this characteristic shape, also used in sails and propeller blades. When an airfoil flies through the air, it is influenced by the fluid's pressure in different amounts, depending on the location. For instance, the top and bottom of the airfoil won't be affected by the same pressure, as with the front and rear. The total force acting on the airfoil is calculated as the sum of the pressure on all of the infinitely small points along the body's surface. If the pressure is the same along the entire airfoil, then no net force is produced. However, if the fluid is in motion, the velocity of the molecules would differ while passing along the airfoil. Due to pressure depending on fluid velocity, it would vary along the surface of the airfoil, creating a net force. The fluid's direction can be defined along the motion. The component perpendicular to the flow is called lift, and is essentially what lifts the airplane, caused by the difference in pressure along the airfoil. The component that acts in the same direction as the fluid is drag, which is the resistance that the airfoil encounters when passing through the air. Observing an airfoil, the center of pressure is the average force that acts along this body while passing through the average point of the object. The center of pressure is also the point in which the net aerodynamic force acts from. In a standard airfoil, the velocity of the fluid is greater when passing along the upper surface and smaller when passing along the lower surface. This means that the bottom has a greater pressure compared to the top, creating lift. The difference in pressure along an airfoil causes torque, also known in this case as aerodynamic moment, which would cause the wing to flip if not restrained correctly. The point along this body where the moment remains constant is called the aerodynamic center, and is much more accurate than the center of pressure in determining aerodynamic behavior. Depending on the wing, which differs by shape, size, and thickness, the aerodynamic center can have varying characteristics. For example, symmetrical airfoils have no torque around the center for all angles at which the fluid meets the airfoil, also known as the angle of attack. Wings that are curved, or cambered, have a torque, and in some cases this moment can vary with angle of attack. After considering the implications of pressure, we can look into the effect that gas molecules have on airfoils. The atmosphere is formed by many gaseous elements, which are disrupted when an object passes through them. This penetration of the air causes aerodynamic forces to be produced, which depend in magnitude on the shape and speed of the airfoil, as well as the characteristics of the gases. There are three main features that all gases have, being viscosity, or the stickiness of the gas, compressibility, or the springiness of the gas, and density, which is a measure of the compactness of a substance. Usually, a higher density of the gas will lead to a lesser compressibility, and vice versa. In order to better understand how these characteristics influence the aerodynamics of an airfoil, aerospace engineers use similarity parameters, which compute ratios between external forces and those generated by the features of the gases. The values of these parameters depend greatly on the altitude and state of the gases, which both have pronounced effects. An important similarity parameter is called Reynolds number, and focuses on the relationship between gaseous forces generated by the viscosity of the fluid and those by the inertia of the molecules. This number is dimensionless, meaning that it is not associated with any unit of measurement, and can range from 100 to 10 million, with larger values signifying lesser viscous forces. The boundary layer is a phenomenon caused by the viscosity of gases and affects the aerodynamics of an airfoil. Essentially, the molecules passing closest to the wing's surface physically stick to it. At the surface, this layer has no velocity, and the speed gradually increases the further from the airfoil we go, until reaching the unaffected free stream in which the fluid's velocity is back to normal. This is due to the molecules colliding with the still boundary layer. The closer to the stuck particles, the more likely the chance of a collision, in turn slowing down the fluid's flow. Monitoring the boundary layer is very complex, as the gas molecules flowing past the airflow treat this layer as part of the wing. In some cases, the boundary layer can separate from the airfoil in certain points, creating a different shape from that of the airfoil's surface. This is due to the boundary layer being unpredictable and randomized in its effects, which is a factor affecting the drag of a wing. Reynolds number can be used to understand the characteristics of the boundary layer. Depending on the size of this value, the layer can be classified as either laminar, layered, or turbulent, disordered. The low-valued laminar flows mean that the high velocity of the fluid increases linearly the further we go from the boundary layer. High-valued turbulent flows mean that the fluid's velocity is inconsistent, and thus non-laminar. The ability of the boundary layer to separate from the wing is caused by pressure itself, due to the weakly energized gases located in these areas being sensitive to pressure variations. When an object passes through a fluid, in this case the gases within the atmosphere, the flow occurs in defined patterns, called streamlines. These fluid patterns, similarly to boundary layers, can be either laminar or turbulent, depending on how much the object disrupts the airflow passing by it. The term streamlining comes from this concept, with engineers purposefully giving airfoils particular shapes in order to reduce drag, which increases performance, and at the same time having the most laminar flow possible, reducing turbulent airflow. This is the reason why airfoils have the characteristic teardrop shape, with the front being rounded and the surface gradually arching back into a thin rear section.